green light. Hey everybody, thanks for joining. The title of this talk is Data Structures for Building Resilient Peer-to-Peer Applications, but I think that's a little bit dry. Instead, it's going to be a little bit going through more war stories and kind of tales from the front lines of building apps that use this model called peer-to-peer, which, if you're not familiar with it, don't worry, I'm going to give a crash course and kind of introduce you to the general ideas behind it. But yeah, I hope it'll be fun and interesting for everybody. I'm Andrew. I'm the CTO of a company called Holepunch. We are the pair people. So if you've been around the conference and you've seen all the pairs and all the things, that's us. We love pairs. The story behind the pair is really just that it sounds like peer in peer-to-peer. There's really no more depth to it. In case you thought there was some deep symbolism there, but we love pairs. We like peers, and we like it when our peers eat pears. So if you go to the booth in the way back of the villa, we have these giant crates of pears for everybody, and so you can eat those and think about the peer-to-peer future. And one thing, this is the third time that we've been at Plan B, and every single time I lose my voice on day one. So that's the tough part about doing a day two talk, is that I might have to talk a little quietly, but hopefully the mics will pick me up. So first off, what do we do at Holepunch? So at Holepunch, we are trying to build apps that can survive the apocalypse, and there are lots of different parts to that, but really, what does an app that needs to survive the apocalypse need to be able to do? So it needs to be able to handle network outages. It needs to be offline first. So if you have no connectivity at all, the app can still work with data that you have available, and it just needs to be super resilient. So anything that can go wrong will go wrong, and this I think it might be becoming more important. Hopefully we don't have an apocalypse in the near future, but certainly, things in certain areas are getting a little more unstable, and I think it's really good to be designing apps that can handle those kinds of scenarios a little bit better. Our seamless communication is going to be super important after the actual apocalypse. I don't know, you probably want fresh water, but at the same time, it's a good engineering exercise to push the engineering forward, to build these kinds of apps and design for the worst case instead of designing for the best case. But the main thing about being apocalypse proof is that there really cannot be any one single point of failure. Everybody at this conference is probably very familiar with not having a single point of failure in a network. But basically, you want unstoppable money, we want unstoppable communications. It's all kind of the same thing. Central points of failure are all over the place, everywhere in the world today. Any service you use on the internet is going to have a central point of failure in the servers. We don't like that. We think that gets in the way. And we also think that with the right technology stack, it's just not needed at all for the vast majority of applications. So that's what we've set out to do, and we've tried to do that by approaching the problem from a particular direction. So we built an app called Keet. It's a communications app. You can get it for desktop, you can get it for mobile. You've probably seen signs for it all over the place. Keet gives you kind of the features that you would expect from just the standard chat app. It has rooms that can be really small, they can be really big. You have video calling or real-time calling in it that all just works without any servers in the way. We have a desktop app that you can use, and also you can get it on the store. You can get an APK if you want to install it on Android yourself. And it might look familiar. It might look like apps that you've seen before, but internally the architecture of the app is massively, massively different. This was really no easy task. We went through a lot of iteration to get there. We've had an alpha version, we've had a beta version. We're getting closer to the 1.0 as we're working out some of the issues there. Definitely encourage you all to give it a try. When you launch the app, you can go into the menu on the side and see some of the rooms that you can join to just join the general pair community, and also to give feedback if you hit any issues. We have a bug bandits room. We have a Bitcoin room, definitely to check out. So you can definitely check that out. And this is our main thing. So we build Keet because we think that chat is really kind of if you can solve chat, you can solve the vast majority of networked applications. It's a very general model, and I'll dig into that a lot throughout this talk as we go through kind of the iteration stories. But yeah, we think that chat is just the best place to start for that. And Keet is built on our second line of development, which is pair. which is a peer-to-peer runtime that you can install. Pair makes it super easy to build apps that you can then distribute to people fully peer-to-peer. So you can put together an app just on your couch, and you can package it up and give someone a link, which is really just a public key or a hash, and then you can download that, and it'll swarm it over the peer-to-peer network, and you'll get the updates from everybody. So that's very, very cool. Pair is totally open source. You can go to our GitHub repo. We have an org called github.com/holepunch2, and you can go there and you can see Pair, and you can also see just tons of docs for all the APIs inside of it. And if you dig even deeper, in order to make this work seamlessly everywhere, we have a JavaScript runtime that we built called Bear. That's really cool. I'm not going to talk about it too much, but it's kind of like Node reimagined and done right, Node modularized. It's very maintainable. There's very little baked into the core system there. So you can check that out if you're interested in JavaScript. And so it's all tons of super cool stuff there. So this is kind of the angle that we've taken to approach building peer-to-peer apps. But if you've never done any peer-to-peer before, I want to just do a little crash course and just describing what the high-level things you need to know about peer-to-peer are. And I think there are really three components that you need to do anything that's peer-to-peer. You need connectivity, so you just need to be able to establish connections to peers. This is like the bread and butter of everything that we do, but connectivity is a very wide space. We're not super opinionated about how you can connect to peers. So in our stack, the main way you do that is through a DHT, a distributed hash table, which you might be familiar with, but it's just a way of querying a lookup table in the network that many, many peers can run, and you can get identifiers for peers that you can then connect to. But really, it's not opinionated. You can use a carrier pigeon, you can use Bluetooth, you can use laser pointers. It doesn't really matter so long as you have some way of connecting to people. And this is, for some applications, this is actually really all you need. So if you go to our GitHub org, you can see that we have lots of tools that really just use peer-to-peer connectivity. So we have a module called HyperSSH is a good one to look at, which lets you SSH into servers just directly over the swarm. And we use it all the time just because it's easier. It's just a lot easier to use. You don't have to do any kind of crazy configuration. You spin up an instance on some node that you might be running somewhere, and you can connect to it by key anywhere without needing to do anything involving IPs or anything like that. So it's easier to use. We have lots of tooling in that space that just use connectivity. So for many, that might be all you need. But then, the vast bulk of the stuff that we spend our time developing at HolePunch are the data structures. So once you have connectivity, you need ways to sync data around. And so we have spent a lot of time building out particular data structures that make it really, really easy to sync data throughout a peer-to-peer network in a very efficient way, where you aren't going to sync more than you need to any one peer, and all peers can contribute to making it incredibly resilient. So if a piece of data has moved from one computer to, say, 10 others, then those 10 other computers can help to make that data available to the rest of the network. And then finally, you have to bundle all these things together to make an actual app that people are going to want to use. And I think this is one of these more understated ones that I'll talk about a lot later in the talk. But it's, you need to actually build app architectures. And when you make a centralized app, you're going to build your architecture around querying a server that you're generally going to assume to always be online. And when it's not, things are going to go very wrong, because usually these are built with the best case in mind. And instead, in peer-to-peer, things are a little differently. The data is going to come from many people. You might get some updates at random times when you weren't expecting them, and you need to be able to handle that. And it's just kind of a different paradigm to work with. So this is like something that you really need to focus on when you're doing peer-to-peer, is actually thinking about the overall structure of the app and making it easy to understand. So we spend a lot of time at HolePunch, trying to iterate on just the general UX of presenting peer-to-peer in a way that people will find understandable, and that's a task and a half. So I'll cover a lot of that. So the talk, it really wouldn't be complete without this classic diagram of what peer-to-peer is. You've probably seen it a million times. It also wouldn't be complete without me apologizing for it. So that's another one. But it's really important because I think it does highlight what you need. In peer-to-peer, in server-based architectures, you have a central point that manages the database, the state. Sometimes this is split across a cluster, but logically it's in one spot. And all the other nodes that are connecting to it are going to be pulling the data from that spot. So I think it's more interesting to look at this less in terms of connectivity and more in terms of data dependencies. In peer-to-peer networks, you don't have that. So you have peers that have the code and the data to run everything running on each of those peers, and somehow you have to make that work by kind of constructing something like a database that's a view over everything. And a lot of our research has gone into that. It takes a lot of iteration to get that right, but that's the main focus. So if you go to our orgs and you start looking at our data structures, you'll notice that all of them are what we call single writer data structures. So you have one person who is the writer of that data structure. So like they're going to make a change to it, and they're going to broadcast it to the whole network. And you might be, if you've used BitTorrent before, it's very similar to that. So the idea is, there you would create a torrent file, and then you could see that torrent file, and the more peers in the network, the quicker you'll download it, because more peers can help out. But there's only one person making changes to it, and a ton of the complexity. You might think that making that collaborative is pretty straightforward, but that's actually where a lot of the tough work is. And so as soon as it becomes a multi-writer system with many people participating, then it becomes a lot trickier, and I will definitely get a lot to that. So definitely that. So that's the general high-level helicopter view of peer-to-peer. I don't want to dive too much deeper into it because there's just a lot more to get to here. So I'll leave it at that. But so here's my first meme. My meme game is just not very strong, so you'll have to bear with me. But my interpretation of this is that somebody said once that peer-to-peer is how you think the internet works before you actually start developing for it. It's kind of like when you have that naivete when you're a kid and you start hacking around with stuff, and maybe you learn about like ifconfig or telnet, and you get the IP for your computer and you give it to a friend and you say, hey, can you connect to me? And they can't, and it doesn't work. And then it's all downhill from there. Like it never really gets better as you become more and more disillusioned with all of the hurdles that you have to face just to make really simple things. And so I really think, on one end, as you learn more about it, you start to realize that maybe a lot of that friction is actually manufactured friction. Maybe the internet was built fully decentralized. Then we had email, which was very decentralized. There were a lot of challenges with managing it. That's true, but not intractable ones. But instead, we started to build these services that really benefit from being very centralized, because the incentives align with that. Centralization means you can make a lot of money, and so it's the kind of thing where, it's the kind of thing that once you really open your eyes to this, I think it kind of changes how you look at the internet more broadly. And I also, I want to take this time just to. We talk a lot about how peer-to-peer is apocalypse-proof, and I think that's true. I think building apocalypse-proof tech is important, but at the same time, I don't find it, it's one of those things that I think is necessary, but maybe not inspiring, in the sense that, like, you want to get excited. You want this stuff to get you inspired to build stuff like this. And I think the motivations for peer-to-peer are actually just a lot bigger than that. I first got involved in peer-to-peer because I was working in this research lab that was sharing scientific data, and I made this service to host Docker containers for scientists, and so that they could spin them up instantly to like verify research from a paper, for example, and make sure that it was right. And I remember just getting constantly messaged at 3 a.m. To come online and fix the cluster because it was down. There was a person who was teaching a class with it, and I wasn't there. And the service went down, and they couldn't teach their class. But the data was right there on her laptop. She just couldn't use the service. And I think the frustration from having to have had to build this massive thing in order to power something that really should be much simpler than this, because the code is here, the data is here, the person that wants to use it is right here, and they couldn't. I really think that's not something that's inherent to the internet. It's actually something that is designed. And so what we're trying to do, along with, as you build apocalypse-proof technology, I think many of the other side effects that come from this are actually just a lot bigger and brighter than that, and will work really well even if the apocalypse doesn't happen. I think another example of this was before Hole Punch, a collaborator of ours made a Twitter clone where the code was modifiable by the end users, and you could distribute it peer to peer. And this seemed like a simple thing, but one of the things that emerged from this was that someone would tweet a new version of the code base itself, and it would kind of virally spread throughout the network, where someone would say, hey, this version's better, I want to use this, and install it as my default. And it was all very frictionless and very creative. And it was one of these things that really just wouldn't be possible unless the developers themselves own the means of deploying that code themselves and can modify it themselves. And this is something that is just a very natural side effect of developing for peer-to-peer. And yeah, it's one of those things that I personally find to be a little bit more inspiring than just the resilience angle. So the idea there is that peer-to-peer covers so many different things and is a different thing to each person. So there are a couple of ways I could approach this talk. I think one would be to dive into technically how we're trying to solve these problems at Holepunch, and I'll get to that a little bit. But I think more interestingly, I think we are in this unique position that I think a lot of companies aren't in, where because there aren't that many peer-to-peer companies, where we've kind of gone through a lot of hurdles over our 3.5-year lifetime to try to get Keat to where it is today and Pair to where it is today. And along that path, new people have joined, and very few people have experience with peer-to-peer. So there's not, there are very few experts that are going to join the company to know about the data models that we use and whatnot. And so you see over and over again that people have certain preconceived ideas of how things should work that they then have to unlearn, and it's a big process. We unlearn things. Even the so-called experts unlearn things all the time, and I think it's really interesting to go through those as well. So this is really what I want to cover for the rest of this is just kind of going through some of those stories that about what it's like to have to build from the ground up an app like Keat, and yeah. So let's start with the first one, which I think. The way I ordered this by meme density. So I'm going to go through the one that has the fewest memes first, and then get to the more memes later. But the first lesson is that data is forever in a peer-to-peer network. So if you are running a centralized service with a big database, you can change the data. You can do a migration to modify it. You have a lot more control over the lifetime of your app as it grows and as you need to scale it. In peer-to-peer, that's a lot harder. That's 1,000,000 times harder. So for us, the scariest word is migration, because, and the reason for that is really this silly little diagram here, which is a cartoon view of what Keat is. So in Keat, the code and the data lives everywhere. And the way we do that is that every single device that's in a room inside of one of our chat rooms has its own data set that it wants to share with people. So it's going to write, and you can kind of imagine this data set as one very long array that you can only add things to. And you write operations to that array, like, hey, I want to add a chat message, or hey, I want to add this new member. And then you disseminate this throughout the peer-to-peer network. And every peer in that room needs to kind of build their own database from all those operations. And we do a lot of things like under the hood to make it so that when you're joining the room for the first time, for example, you don't have to over-download huge amounts of data. But that's generally the idea for how we build these things. And you can already kind of probably anticipate some of the real challenges here, because there is no one view of what's going on. I'm going to have a view of the network that's dependent on the peers that I've seen and I've been able to connect to. Another person in the room is going to potentially see something else, and this is really tricky to manage, because especially from a UX perspective, because somehow you have to explain to peers that that maybe what they've seen in the database before or in the room before is going to change. So the goal here, though, is that over time, as more and more peers connect to each other and as the data spreads around, eventually everybody will see the same thing. And this is what we strive for with the algorithms that we build, but that is very tricky. And one of the big reasons actually why that's tricky is because with Pair, we have this runtime, this really powerful runtime, where we distribute Keat over Pair, and Pair makes it very simple for us to ship new app updates. So whenever we change something, we can just click a button and it'll distribute throughout the network. And this makes it very seamless. The problem here is that updates come in many, many different categories. So you can have updates that just change something superficial, like maybe the styling for how a chat message looks. But then you can also have updates that modify the actual way that we convert that array of operations into a database. And so these are the really, really difficult ones to ship, and we've hit a million problems trying to do this in the past. And so I want to just kind of explain, so if you're in our position and you need to make a change, what are the steps you need to take to actually make it safe? Because when something goes wrong in peer-to-peer, and I think this is one of the hard lessons that we've learned several times, when something goes wrong, it's kind of like when something goes wrong in Bitcoin. When you sign the wrong transaction, you've signed it. It's signed, and now the room can potentially be in a corrupt state that you can't really recover from without violating the contract somehow. So what do we do there? And this one is kind of tongue-in-cheek, but you do that with a lot of careful code review. You really have to make sure you need to split the changes up into ones that cause persistent, that update the persistent data in your app, and you need to change that, and you need to split it into ones that are actually just much simpler and change the superficial stuff in the room. And there were many cases, but this works a lot of the time. Everybody has to do this, so it's not really unique to peer-to-peer. But we make mistakes with this all the time. So when we were developing a feature that we're going to be releasing soon after this conference, DMs, so you have direct messages, we accidentally ran one of our experimental builds on a couple of production rooms. And it's one of these things that's all too easy to do, because testing peer-to-peer is actually a pretty unique challenge, because a lot of the time you can test a lot automatically, but because this runs on different devices and different crazy networks, you're just not going to cover all the cases. And so, one of the things, so you actually do need to run this on live devices in the world on real data in order to actually verify that the features work. And can we get stronger guarantees than this? Because this is not, you can imagine this is not a foolproof process. So we have spent a bunch of time improving the data model in the rooms to make it so that you actually just get a lot more guarantees. We used to make it so that our app upgrade lifecycle was perfectly tied to the pair update lifecycle. So you ship an app update, and all the apps update. Now they're using a new data model. This is mega problematic because peers update at different times. You can't just, it's not like a website where you can bring the website down for an hour, do an update, do a migration if you need to, and then bring it online. You can't do that in peer-to-peer. Instead, you ship an update and it propagates gradually. So peers are going to upgrade themselves at different times. And the way to solve this problem is actually to kind of invert it a bit. Instead of saying that we choose when you upgrade, we ship an upgrade, and then the peers choose when they want to apply it. And so the idea here is you make all the new code available, and the room itself, the actual data structure, says, hey, I want to speak this version. And at a certain point in time, the members of that room can then choose, saying, okay, we're going to now move to this new version, and there's going to then be consensus around that when they choose it, so that you always will know what a room is speaking. And this has been a big unlock for us. We've used this to design what we call experimental mode, which makes it really easy to ship features super quickly, because it means that you still don't want to be fast and loose with anything that modifies the schemas, but at the same time this gives us a lot more safety guarantees because we can control exactly when we want. In the room logic itself, we can control when updates are applied. So very powerful. This is a really cool unlock that we've recently got. We used it to do this DM release that should be coming out soon. So stay tuned for more info on that. And another interesting thing about peer-to-peer is that because the data lives forever, you're going to have clients that are running extremely old versions of Keat that are using outdated schemas and all the craziness that comes from that. And you have to design for that. When you make a new version of Keat, you have to design for the idea that older people are still going to be around, and that new version needs to make sure that it can handle the older schemas. This just makes it slow to iterate. This means that when you want to make a change to, say, the way a member is represented in the room database, you have to be very careful about how that gets shipped and when you choose to view messages that use that new schema. So we've done a lot of iterating as part of some of the newer releases that are coming out soon. And we've come up with something better, because that whole process is too much work and it slows things down. And when you have a super tight development timeline, you need to have a better model for this. So the general idea here is that through the development of Keat, we've gone through a lot of iterations on this internal database that we have, and we started with one that was a little I wouldn't want to say poorly structured, but structured specifically for how Keat should function, because we didn't really know what the problems were at the time. And then for the beta release of Keat, we added a lot more structure to it that made it much easier to upgrade things. But it still was really not bulletproof, and we still got stuck on trying to test out new features. And now finally, we've actually, kind of strangely and surprisingly, we've converged on a new design for a database that solves this a lot more generically for any kind of app that you can build in peer-to-peer. And it really looks a lot like MongoDB, if you've ever used MongoDB, which we think is a really good sign, because that means that maybe we're hitting a simplicity bar that people are going to be able to understand very well. So it's one of these things that as you iterate more, you might start more specifically to the application you're building, but as you go through all these hurdles in the development process, eventually you'll wind up with something that is just a lot more intuitive to work with, while also solving all the hard problems in just a much nicer way. So this has been a really big part, and so we're excited to get this out in one of the releases coming up soon. Another huge thing beyond the data that is something that we always get tripped up on all the time is that large scale is paradoxically a lot easier to manage. And in a centralized service, if you're running just a standard app on a server, the smaller the better, because if you have 2 users, it's just a piece of cake to spin this up. You don't have to spin up a crazy cluster to manage a million users and all the different varying traffic loads you're going to get. It's just it's a bigger mess in centralized apps. So in peer-to-peer, it's the exact opposite. It's actually the case that the smallest networks are the hardest things that you have to work with in peer-to-peer, and larger networks are much easier. This is not unique to peer-to-peer, because there are many social networks and stuff that have bootstrapping problems where you have to get to some critical mass before things work really, really well. But in peer-to-peer, it's just a lot deeper than that, because the network is powered by peers. So if you have a network that's really tiny with very few peers, it's like a moped. It's underpowered, and it can't get up the hills. It'll still work. Eventually it'll get up there, but it's not going to work as well as it would if you had tons of peers helping out. So yeah, this is so bigger is a lot better in peer-to-peer. And so why does this really require unlearning? What's the big thing in this? And why also are smaller networks so much harder? Well, the biggest one is just data availability. We can't beat physics in peer-to-peer. So if you have a 2-peer network and the data only lives on one peer, the other peers aren't going to get that data until that first peer comes online. And that's just something that we have to work with. You can't change that. The main thing that you can do in that scenario is just to make the network bigger, and I'll talk about that in a second. But there's one other really big thing that makes bigger better, which is bandwidth sharing. So in peer-to-peer, when you're sharing these arrays or these data sets with other peers in the network, if a peer has that data, it can reseed it to other peers. And this means that the more peers that you have, the stronger things become and the faster things become, because you have a larger network of peers to help out. And this has helped us a ton when it comes to things like file sharing. But it also, it just means that the network is going to work a lot better when there are more peers around. So what do we need to do with those small networks? Well, we need to just make the networks bigger wherever we can. And there are a lot of tricks for how we can do this. We have these fully encrypted mirrors that we can use that any peer can run in the network. Any peer can become a mirror. And by using these mirrors, you can really make it so that even if you have a 2-person network, it's always going to function. So one scenario that we hit early on in Keat, in one of the first versions of Keat, we have a pairing system. And I'm realizing I should step back for a second and talk about what pairing is. But pairing is this process of getting a new member to join a room, right? So you share a link with that person, they click it, and now they can become a member of the room. And in the early versions of Keat, this was a super interactive process. So all the peers had to be online at the same time, or at least the person who was going to add you to the room had to be online at the same time in order to get the data. This didn't work. This didn't work really well. So instead, what we did is we came up with a new pairing system that actually used the DHT to make it fully non-interactive, so that peers could come online and offline at different times, and everything would still work well there. So this is another example of kind of using other peers in the network to also help with pairing as well at the same time. it touches all the sides of the stack. One cool thing here that is going to be possible soon beyond this, that we haven't had the ability to do before, is piggybacking on larger rooms. Just to, so if you have a 2-person room, but you're also a member of, say, a 1,000-person room, you could potentially piggyback on that to make the network a little bit bigger. So we have a release coming out soon that's going to include DMs. And the way you establish a DM with another person is that you send an encrypted message through a larger room to send an invitation to them so they can join that new room. We can actually just use that same machinery to potentially exchange encrypted messages through a larger room. But that also comes with downsides, because that means that the people in that larger room are going to have some metadata about who you're communicating with, not the contents, but how many messages are being sent. And so this is really kind of a broader point about the trade-offs that you have to work with when you're designing these things, because for some use cases that might be perfectly fine, and then you're going to get this ultra reliability kind of for free. But in other cases where you care a lot about security more than anything, that's not going to be privacy more than anything. That's not going to be the dominating thing. So that's a theme. But this is a broader thing. There's a theme here, which is that hard is easy and easy is hard. And this is one of those things that is really easy to say, but very, very hard to internalize. Because we hit this all the time, and this is actually, I have a lot of things to say on this one, because it's very expectation defying. It has this real way of flipping what you would expect on its head. So jumping into the first thing here that I think is really interesting, we were able to add file sharing to Keat extremely easily. But at the same time, we recently did this release where we gave people the ability to leave rooms, and we released it with a lot of fanfare. We finally have leave rooms in the app, and this is one of those things you would expect to be in the v0. It would be the first thing you would add, because in a centralized app, leave room is just a database update operation. It's the tiniest thing you could possibly do. But for us, it was a huge, huge, huge engineering cycle, and it took a ton of work. And it's the kind of thing that, when you have to explain to people why that is, it might not be immediately obvious. So first off, starting with the file sharing, why was the file sharing super easy? Well, it's because to share files, you can share them the same way that we distribute apps in pair. We already have all this infrastructure in place to distribute files from any peer in the network to any other one, where each peer can verify that data and make sure that it's correct. We've invested a ton into that machinery. So we were able to add file sharing to Keat where there are just no limits, almost for free, just because it's a side effect of the other stuff that we've made. So we prototyped that in a weekend with a couple of developers, and the version we have now is pretty much that same version. It hasn't gone through that many changes. It's just that code, and it just works because this is peer-to-peer. Peer-to-peer gives you this super easily. But leave room, on the other hand, is wildly different. So with leave room, we had to make a change to our consensus engine, which means the way we take all those messages that peers are sending in the room and converting it into a database that is consistent for everybody in the room. We had to update that to take leaving into account. And we spent a ton of effort to make that consensus engine scaled from to 1 million peers. It's the kind of thing in the Keat alpha version, it scaled to maybe to a much smaller number than that. And we went through many iterations in the beta to get it to basically be an unbounded number. But we didn't consider the leave challenge too much. We didn't. It just wasn't part of the initial push forward. So so we had to actually get that in. And any change to consensus is super, super scary because of the stuff from before, where the code and the data live everywhere and has different versions. So that's just a super consequential thing. And we had to go through lots and lots of iterations to actually find a way to make that correct. And for identities, so we recently did this release in Keat called the Identities release, which adds persistent IDs to your app, which means previously when you wanted to join a room from many devices, all the devices would appear like they were separate users, and then we added IDs, which simplifies a ton of stuff. Internally, IDs are just rooms, which is one of these really cool properties of peer-to-peer, where we can reuse all of our stuff in many different ways. But we had to update, when you leave a room, it has to be synchronized across all your IDs, because you can imagine, what if one of your devices was thrown into a lake? Well, then you might be partially, because these different devices are all joining the rooms independently, you might wind up in these weird states where, you're kind of in the room and you're kind of not. And so going through, this is all just to say that with IDs, leaving is extra hard also because you have to synchronize it across many different things. So leave room, really, really difficult. File sharing, super straightforward. But what's cool about this, though, is that because we've solved leave room in Keat, that means we've solved it in any kind of collaborative social peer-to-peer application that resembles Keat. So if you wanted to make something like a peer-to-peer Reddit clone, for example, and you wanted people to be able to leave communities, it's the same problem. It's the exact same system, and you can use all of our same tech to solve that problem as well. So this is one of the cool things. We're going through a lot of these iterative processes, and we're getting them wrong at first and then getting them right later. But once a problem is solved in Keat, it's solved in general for pretty much any kind of social peer-to-peer app that you want to build. So this is just one of the great things about this whole process. Another thing that I want to talk about here that sounds easy, but is actually really hard, is making UIs. Here's more of my very outdated meme game. But one does not simply make a UI. A UI is a tricky thing to build in peer-to-peer because that database underneath the app is changing in ways that you might not expect. So without going into the details of it, one consequence of this consensus engine that we use to generate this room database is that some of those operations might reorder and change things. And this means that when you're viewing a chat, suddenly chat messages might appear out of order. And this is, it's kind of like the Bitcoin mempool in that way. There's the challenge here is that, how do you convey this to users that this is an expected thing that happens normally in a room? B, how do you handle the side effects of this? So like say you have, taken some action based on the ordering of a message and then it's gotten reordered. Somehow you need to get some confidence that that an ordering is going to be stable. So yeah, this is all just to say that conveying reordering to users can be a complicated thing. If you look at Slack, if you've used Slack recently, it's been an absolute mess because when you send messages and you don't have connectivity, sometimes it might be grayed out, and then at a later point in time, it's going to be sent, and it's not going to indicate when that message was sent originally, or it's just going to end up being incredibly messy, and it could lead to a lot of confusion. And so this is something that I think that the bar is actually higher in peer-to-peer than it is for centralized apps to build this out. And it's just something that we have to work with because in our stuff, again, we have to design for the worst case instead of the best case. Another interesting thing that people don't really necessarily understand the complexity of here is that it's just showing something as simple as double check marks next to messages just to know when they're going to be available. And I think it's worth digging into, what is a double check mark? When you send a message and say WhatsApp and you see that, what are your expectations? Your expectation is that the user is going to be guaranteed to get that message at some point when they look at their app next. In small rooms, in two-person rooms, there are probably ways to do this that would make sense and would be intuitive to people. You could say the recipient of that message could write something down saying, hey, I've received it, kind of like a read receipt. But in larger rooms, that approach doesn't scale. And also, the general concept just breaks down because what does it actually mean to guarantee delivery to a network of 1,000 peers who are coming and going at different times? So this is something that is just not simple. And it's not simple to actually design the UX that even captures that concept well in a large room. And it's something that we're iterating on. Right now, we don't have any kind of checkmark in Keat, which is, we're thinking about different kinds of approaches to that problem, but we haven't done anything yet because of these potential problems. But an example of something that's really easy is joining massive rooms super quickly. So in Keat, if you pair with a room that has a super long history, like let's say that room database is 20 gigabytes because there's years of history in this room, you as a new user will join immediately because we've spent a lot of time investing in those data structures to do that, and we call it sparse downloading. This is something that you might think would be incredibly challenging to do. A lot of other peer-to-peer apps or a lot of would actually just have to download that whole database to generate the whole thing yourself for every peer. But for us, this is like a really core part of our stack, and it means that it was just kind of a natural side effect of what we could do in peer-to-peer. So here's that's another use case where your intuition for what thing is going to be easy and what thing is going to be hard really kind of has to be turned on its head. and this is just a little cartoon. My cat is actually perfectly fine and perfectly non-existent. But I thought this was a good example because, if you send a message and you don't actually indicate when it was received and you send a reply, you have no idea what the context is. And because in peer-to-peer this happens a lot more than it would in a centralized app, you're just gonna, we have to design for this, and other apps don't. So, but hopefully once we solve this problem in Keat, it'll be a very general thing that will apply to anything, and that's why we put in all the hard work to do that. So a lot of head scratching went into this, but when we come up with the data structures and the algorithms to power Keat, and when we go through our different iterations, these things are released. The core internal logic that powers all this stuff is all released as open source on our repo, and you can use it inside of Pear. So it's the kind of thing where when we do this hard work, hopefully everybody in the community it'll make it easier to build this broader set of apps. I hope that made you a little bit more excited, maybe more terrified of peer-to-peer, but hopefully a little more excited than you were before. I want to say that everything here is the result of just a super big team, and the vast bulk of that team is here at this conference. So if you look to your left or your right, you will probably see people on the Hole Punch team. Yeah, right. Thank you. So direct your questions around, find them in the crowd. I was going to say that the pairs are a good sign, but lots of people are wearing pairs. So you might have to dig a little deeper. But I'd say the last thing to unlearn, especially with related to peer-to-peer, is that finding talent is easy because it's not. So if any of this excites you and you want to solve these hard problems, and your blood pressure is like at a healthy level and you think you can handle that, then go to this site and apply, because it's tough work. It's really satisfying work, and the team is amazing. So really, if this interests you, just come seek us out and talk to more. And yeah, so that's what I prepped. But thank you all very much. And I think there's time for questions, I would hope. Hey, yeah.
You said that
I think you need to get a mic. Sorry, I was supposed to say that.
I can scream it. You said that. Hello.
Hello.
You said that the data is forever.
Yeah.
But it's hosted on all the different peers.
Mm-hmm.
Does that mean that basically your computer space gets smaller and smaller the more rooms you join and so on?
So it's a tricky problem. It is a tricky problem.
And second question, would there be a way to delete all of that data?
Yeah.
At least you're personal. Let's say I want to delete every message that I've ever written.
Yeah.
And I just even want to delete my account and everything related to me.
I'll do the storage space one first. So on the storage space side, you can definitely clear up space. If you go into Keat, for example, if you've uploaded really big files, we have a button to clear all of that. For the chat messages as well, once it's a little bit more technical, but once it's been seen by a lot of people in the room, it's very, very safe to clear it, and that'll be totally fine. You can also, even if you're going to leave that room completely, then you can also fully clear the data. So say you leave all of your rooms in Keat, or you leave a room, all the data associated with that room will be cleared. So stuff like that, that's straightforward. I forgot the second question.
Yeah, basically my question is basically cyber trash, I guess, how to avoid that, how to avoid creating loads of megabytes of information that isn't even needed or used anymore.
Yeah. It's all clearable, and we have the tools to clear that. It's one of these. It's a hard thing. Deletion in general is actually very tricky because if you're in a massive network of 1,000 people and somebody has downloaded a piece of that data, so these are all on different people's machines. It has been downloaded by others, so you can't force them to delete it. That's why deletion is just in general kind of a tricky problem with a lot of nuance in peer-to-peer. But when it comes to the storage space problem, yeah, you can clear all the stuff you have on your computer, and that's fine. It's a lot more fine if you've reseeded it to somebody else in the network, because otherwise, if you have the only copy and you delete it, well, nobody else will be able to get it. That's just that's how it works.
So no peer-to-peer cyber trash.
No peer-to-peer cyber trash. Yeah. Any other?
Yeah. Also, I have a bunch.
Hit me.
So, how many data structure iterations did you have, and why do
Yeah.
you think that is?
Well, okay, so yeah, the question was how many iterations have we had on the data structures? I think we have like this unofficial. I don't. It's not a rule, but it's like a saying that the fourth time is the charm. Like for pretty much everything. Like you do one iteration where you have no idea what you're doing, and then you do a second iteration where you're like, wow, that first one was trash. Then you have an aha moment. You're like, okay, the third one, I nailed it. I got the concepts. But it wasn't an aha moment. It was an illusion. And then the fourth one, you get something that at least looks like it's solved all the right problems and has been
Even if you're still a skeptic about it.
Yeah, even
I
if you're
guess.
still a skeptic. It seems like 4 seems to be the magic number for a lot of our iterations, but I don't think there's no upper bar.
All right, thanks. And then, how much time does it take to exit the room?
Well, it should be instant to exit the room. There's no consensus that is needed to exit the room. So it's kind of like leaving a room can be broken down into many things, right? So in one case, you need to if you want to force leave a room, for example, that should always be possible, even if nothing else works in the system. You should always be able to leave a room uncleanly. If you want to cleanly leave the room so that everybody else in the room can see that you left, you need to send a message to the others saying, "Hey, I'm going to leave it." There's no time limit for when you can leave after that. But yeah, it is something that has to actually be gossiped to other peers in the room.
So the first case is where you mute the room, actually.
Yeah.
And the second case is where you make everybody aware that you left.
Yeah, exactly. So it's much nicer to do that. You can also mute the room without leaving it. So it's kind of like you can break down the idea of leaving into many different categories too, which is what makes leave another thing that makes it so hard. But you can always in case the clean machinery doesn't work, you can always force leave, and what that's that's just gonna say like I want to clear this storage and remove it from my list. So yeah.
All right, and then about the order, what is the problem about just timestamping a message?
Yeah,
Why you cannot do that?
Well, you can't really. So that's a general problem of just timestamps in general in like distributed systems. You might have a system clock that is shifted an hour into the future, and you could potentially use that to attack the room or to send a message that looks like it came at a different time.
Right.
So timestamp ordering is just never super reliable in peer-to-peer because like there really is no such thing as time in this state. So we use something else called like a vector clock. It's like another way of establishing which messages you have seen, and we use this to kind of build a graph that we can then work with. So that's the better way to do ordering in peer-to-peer.
All right, thanks. Last one,
Mm-hmm.
I promise. And so how do you handle shade mirroring when you are in a mobile OS and the apps are not able to do anything in the background?
Sorry, what was the question about? Was there something
I hear
mirroring?
you are making some shade mirroring. Or
Shade mirroring?
blind mirroring?
Oh, blind mirroring. Blind mirroring. Sorry, yeah, exactly.
Was not sure of the term.
Yeah, that's an interesting one because like as soon as you background your app on mobile, it's suspended and all the networking is done. So if you write a message, because all these data structures are local first, and you're not sending them to any server somewhere, you're just writing it to a local log. And if you close the app immediately, it's not going to get sent to any other peers in the network. So what you need to do there is have some indicator, like a double check, basically, or a check that says this is safe. It is now safe to close the app. And the way you could do that, it should always be configurable. Those things should always be configurable by users. But you would want to get some notification from some other peer that they have seen it. And it could be as simple as just saying, hey, this message has left your device. That's one way to do it. There are other ways that involve things like read receipts you could add, but that's the simplest.
Right, thanks.
Yeah, no problem. Thank you.
Question about privacy. So, should Julian Assange use Kit for communication? What are potential threats?
Yeah, that's a heavy one. I think there's a difference between anonymity is almost kind of a separate category in itself. So when you use Keat currently, we use a DHT that's very similar to the one that's used in BitTorrent. So if you join a swarm for a given room and you connect to lots of peers in that room, you will see those peers' IP. If you want some way to get like full IP privacy as well, you probably need to layer this on top of Tor or use some other tool that would give you like a lot more anonymity guarantees. which is to say that anonymity has not been an extreme focus for this. We still want to validate all the core stuff when it comes to resilience and just the general security and all that. But yeah, so I would say probably not for pure anonymity right now, unless you're using other tools or using it on Tails or something. Yeah.
Beside IP stuff, other threat you mentioned in the presentation that there will be in the new release, right? When there will be improvement in transferring data, right? Using big rooms, right? There's another. That's also is a threat, right?
Well, that's an experimental thing that we might play around with, that we would have to have a lot of warnings for before you use it. So you could, for example, if you wanted to have have DMs that are always super, super reliable, you could send those as encrypted messages through another room. But there will be metadata leakage in that, because everybody in the room is going to be able to not read the contents, but see, hey, this peer has written this record into the database, this encrypted record. If that metadata is super important for you to not have, then you're not going to want to use that kind of a system for that. And we would have to make that very clear in the UX if we ever added something like that. So, yeah.
Thank you.
Yeah. Cool. Any others?
Yeah, I have a question about how do you approach testing, because in a centralized backend, so to speak, it's one of those problems that seems simple, but in P2P seems a nightmare. So I was just curious about...
Yeah, testing is really, really hard. We have all of our modules that we build. We believe in modular development, so we have tons of modules. And if you look at our repos, we have our GitHub org, you'll see hundreds and hundreds of repos, and each one of those should have tests inside of it. But they're never going to go all the way there. If you actually want to get to the bottom of peer-to-peer issues, you need to test it on real networks with real people. That's tricky to do, because you also you need to balance being able to test on real networks while also not corrupting data. This is what I was trying to get at with that experimental mode thing that we added recently, which means that the room is going to declare what code should be used to run that room, which means you can kind of isolate those changes a lot more effectively. This means that we can ship out updates without needing to worry about too much, even on real networks with real rooms. And the rooms that are experimental, it's a mode they have to set. Like, hey, I'm going to be in experimental mode room now. We could test changes on those rooms without it affecting any other production rooms, for example. But it is just a really hard problem in peer-to-peer, because testing is tough. Another thing that's really tough about that is we can't actually collect any logs or any information about what's going wrong on users' computers. So if some network in some country somewhere is blocking UDP, we're going to have to rely on reports coming through other channels to report that, because maybe they won't be able to use Keat currently. And that's just a general issue. Collecting any kind of that data would have to involve consent, and we have a lot more. We have a lot more restrictions there. So that's a hard problem. That we kind of rely on people reporting issues through other channels for those particular kinds, and we use experimental mode to test more standard releases. Yeah.
Awesome. Thank you.
Thank you. Cool. Anything else?
You can.
But I love Keat. They have so many questions. Please, Andrew, can you re-explain the UDP thing versus the TCP, and can you diss Nostr for us a little bit?
Well, not the second one. So when you use our DHT module Hyperswarm, it's a DHT with a bunch of extra goodies in it. And so it's a DHT that also gives you the ability to hole punch to other peers. That's kind of the backbone of our peer-to-peer network. And that DHT uses UDP. When you establish a connection to somebody, it uses UDP, and it uses UDP hole punching to do that. The way hole punching works is, you have two peers on private networks, and you need to somehow find a way to get through the firewalls on those two networks to connect them, and that's much, much easier to do with UDP. Yeah.
It is on a lower layer than Twitter is built.
Yeah. So these are transport protocols, right on top of IP. So IP is the lowest layer, and then you have UDP and TCP are different kind of transport protocols. TCP gives you ordering, UDP doesn't. It's just blasting people with these unordered messages. So we use UDP as the backbone for all of our stuff. Yeah, you could build a lot of this also on TCP. It's much harder with the hole punching, but yeah, we use UDP. And we have a protocol. You can look on our org, or GitHub org. We have a protocol on top of UDP called UDX, which gives you, it gives you a little of the features of TCP, but it's designed mainly for running on top of our peer-to-peer stack. So it's very tailored to what we do. But yeah, that's it.
Too many questions. Thank you very much.
Cool. Mm-hmm. Mm-hmm. Yeah.
Yeah, thanks for the talk. It was great.
Thank you.
For the database that you talked about, is a graph database. Is that a new algorithm that you came up with, or is it existing technology? And is that going to be open source? And
it is all open source. So we don't build a graph database. I was mentioning we have kind of a causal graph of operations, but we don't actually construct a graph database out of it. The algorithm that we use is called Autobase. It's all open source. You can go to GitHub and check that out. The general idea behind this is, every single peer in the network is just publishing this array of operations, and then we need to find some way. We basically do, if you do functional programming, you want to do a flat map over all those arrays to make one big array, and then you want to reduce it into a database. That's what the algorithm does. And then, there's a lot of work and a lot of research in that to try to make that, eventually consistent in a really nice way so that everybody sees the same database in the room. But yeah, that's the backbone, and it's all on GitHub, and you can check that out. I think we're doing a big push on docs, and one of those things is to really thoroughly document Autobase. So that's something, if you look at the docs there, it might be a little outdated, but soon it should be good to go. Yeah, cool.
Hi Andrew, Parag here. So I wanted to ask about the new DB which you are launching, the HyperDB. I've been using the Hyper-B before this, and I can see that it was only append only. And now migrating to the HyperDB, will it be backwards compatible, or?
Well, they're kind of two different things. So HyperDB is a database layer on top of Hyper-B. So all the databases in the world, for the most part, are built on top of B trees, like Hyper-B. And HyperDB is just a layer on top of this for doing things like building indexes and querying over indexes and collections. But internally, it is all Hyper-B. So it's kind of like, when you say compatible, you won't have any existing Hyper-Bs that use the HyperDB schemas and formats, but it's the same data structure internally. Yeah.
Yeah, but if the Hyper-B has the data, if it has the historical data, can we add queries to it when HyperDB is added?
You would have to reindex it. You would have to go through all the keys and values and reinsert them into this new database, because we use a whole bunch of new schemas for that. So it wouldn't just be plug and play there, but you could migrate it for sure. Yeah.
Thank you.
Mm-hmm. Cool. Anybody else? All right. Awesome. Thank you all. Appreciate it.